Okay, welcome back, everyone. Let's start again with Andrew, lecture 3. Andrew, take it away.
Great, thanks. All right. So, hey, everyone. Let's see, a quick recap of where we left off. So yesterday, we started off in the first lecture, sort of reviewing the kind of basic cosmological motivation for going after probes of large-scale structure in the nonlinear regime, and how that really required some additional modeling on top of sort of root-level theoretical modeling, in particular models of the galaxy halo connection, to connect what we can predict with sort of fundamental theoretical tools to what we can actually observe. And then in the second lecture, we talked in some length about a particular form of the galaxy halo connection, abundance matching, in which basically subhalo mass, or some proxy for subhalo mass, is assumed to be in monotonic correspondence with galaxy mass, or some proxy for galaxy mass, like rest frame luminosity in a particular band. And we sort of saw that there's a sort of wide range of successful predictions that come from that basic non-parametric model and assumption. And the real takeaway was just that despite the enormous complexity of galaxy formation, that at some level, this key assumption must be correct, that that sort of deeper potential wells correspond to more massive galaxies that live at the center of those potential wells. That there's a relatively tight scatter, about a monotonic scaling relation between potential well depth and galaxy mass. And one thing that I noticed that I slipped up on many times yesterday was I would refer to abundance matching as the stellar to halo mass relation. And I think it's very common for the field to just sort of generally refer to these two things as essentially synonymous. It's because abundance matching gives a non-parametric prediction for what the stellar to halo mass relation is, the scaling relation between halo mass and galaxy mass. And it's quite simple, this scaling relation over a wide range of redshifts. So what you're looking at here is a figure from a paper led by Peter Baruzzi, in which he used abundance matching to match galaxy stellar mass functions across a wide range of redshift. As you can see, at least over the range of redshift from 0 to 2, 3, or 4, there's really very little evolution in the stellar to halo mass relation that emerges from abundance matching. And so even though the physics of galaxy formation changes a lot over this timescale, the stellar to halo mass relation remains relatively stable. And I should just say that this is a very robust result. So many authors approach this particular problem of deriving constraints in the stellar to halo mass relation and arrive at the same result. In this version of looking at the stellar to halo mass relation, the y-axis is actually not stellar mass, but stellar mass divided by halo mass. And you'll see it has this characteristic peak at around 10 to the 12 halo mass, around Milky Way halo mass. And that peak just corresponds from the previous figure to the sort of the knee, the turnover in the slope. But here plotted as the ratio, you see that there's this very robust peak in what is commonly referred to as star formation efficiency in the field. So I want to sort of raise a warning flag to be careful and be aware that star formation efficiency is kind of an overloaded term in the field. So depending on context, people will use that same term to refer to slightly different quantifications. I'll give an example of that in a few more slides. But it's certainly a reasonable interpretation of this peak, that basically around this characteristic halo mass of 10 to the 12, you have a sort of highest ratio of how many stars you have per unit halo mass. And again, so this is a robust conclusion derived by many authors. And it's so robust that we now use it to essentially to calibrate hydrodynamical simulations. It's now a sort of classic diagnostic for how well you chose your feedback prescriptions when calibrating your, when tuning your hydro simulation. So what you're looking at is it's a figure by Annelise Pilepic from a few years ago, in which this was the sort of release of the illustrious TNG hydrodynamical simulation, which was a sort of major improvement to the illustrious hydrodynamical simulation that preceded it. And again, you're looking at this characteristic stellar to halo mass ratio. The sort of the gray bands that are sort of in the background in this figure are the abundance matching derived constraints on the stellar to halo mass relation. And the black curve, which is in good agreement with the abundance matching constraints, is the illustrious TNG relation. So this is a purely emergent relation that's not put in by hand. It comes from a result of the enormous complexity that's captured by the illustrious TNG simulation. And you can see comparison to the red curve, which is the illustrious simulation that preceded TNG. The black curve is in much better agreement with the abundance matching constraints. And so this is a sort of classic example of the way in which empirical models are used as a guide for much more complex physical models of star formation. And one sort of key sort of interpretation of the thing we've gleaned over the past 20 years, sort of having this hand-in-hand relationship between abundance matching and hydro simulations, is that at the low mass end, there's this really completely different physics that shapes the slope of the scaling relation in the stellar to halo mass relation. So it's star formation feedback processes like supernova and stellar winds and various coupling strengths that impact those physical processes have a large effect on the stellar to halo mass relation. And abundance matching in the low mass halos gives a nice guide for how feedback parameters can be tuned in order to agree with sort of the scaling relation that we know must be true from sham. And then likewise, at the high mass end, those processes simply don't have enough energetic power to change the stellar to halo mass relation in very massive halos, but AGN do. And so again, at the high mass end, the stellar to halo mass relation is also used as a diagnostic to inform how implementations of AGN should be tuned in hydrosims. Okay, so I promised another example of an overloaded use of the term star formation efficiency. So this figure, so in a separate paper led by Peter Baruzzi, shows as a function of cosmic time and halo mass. So this is a 3D plot color-coded by star formation efficiency, which is defined in a different way. So if you sort of carry out abundance matching from redshift to redshift to redshift, you can sort of infer on average what the average star formation rate is in order for a galaxy of this mass to have formed a galaxy of this mass across the given time step that you sort of did the finite implementation of abundance matching. So you can infer the average the star formation rate across time. And you know from simulations, you can directly measure in a simulation the mass accretion rate on average for a halo of a given mass. And then the ratio of these two things, the star formation rate divided by the halo mass accretion rate, tells you what fraction of the accreted mass is being transformed into stars. And so that fraction is what's here color-coded in this plot. And there is a remarkably sort of simple takeaway from sort of formulating the results of abundance matching in this way, which is that there's essentially no evolution in time for the peak of star formation efficiency. This yellow band is essentially horizontal for most of cosmic time. And so a simple bumper sticker takeaway from this is just that stars tend to form in Milky Way halos. So most of the stars in the universe formed in a dark matter halo of mass 10 to the 12 for almost all of cosmic time. An important caveat to this is notice that there is a steep downturn at high redshift. So this result was from 2013. So this was before the era of JWST. And JWST is certainly upending our understanding of star formation efficiency at high redshift. And so this high redshift regime is certainly still up for grabs for getting tight constraints on star formation efficiency. But for certainly most of cosmic time, most of the stars formed in the universe today form in Milky Way mass halos. Okay, so for purposes of today's lecture, I wanted to sort of tie up loose ends with the stellar to halo mass relation. And I really wanted to kind of do that as a device to really talk about differentiable programming. So for those of you who will not go on to work in the galaxy halo connection or cosmic structure formation, you may find sort of emerging computational techniques from essentially AI/ML libraries that are becoming much more widely used in common, very useful in your research. And so I wanted to essentially walk through a little bit of the stellar to halo mass relation to introduce the parametric form of the stellar to halo mass relation, and then to sort of give you a preview of the sort of differentiable techniques you can use with modern libraries to implement that, and then to sort of optimize a model sort of using modern methods. So quick, one last word of context about the parametric form of the stellar to halo mass relation. So in fact, most of the results that you will see in the literature on when people refer to abundance matching, they typically are not using the kind of deconvolution non-parametric form of sham that we talked about at some length yesterday. They're using a parametric fit to sham. They're using essentially a broken power law that's sort of smoothly rolling power law whose slope turns over around the characteristic halo mass. So what you're looking at here is an example of a sort of smooth stellar to halo mass relation. It's essentially a parametric fit to non-parametric sham. That's convenient for purposes of introducing you to some basic techniques in differentiable programming. And also, and I'll talk about this a little bit more in the next lecture, it's a parametric formulation of abundance matching is just more practical for doing sort of kind of honest uncertainty quantification when doing large-scale structure measurements. So in the level of precision that Will had shown in the slides yesterday, non-parametric abundance matching is nowhere close to being that accurate. So if you sort of chi by eye looks reasonable, but there's just nowhere near enough parametric freedom and flexibility in order to meet DESI level precision in galaxy clustering. And so the idea then is to use sham to give us the general shape of what a functional form should look like in order to give a good description of the stellar to halo mass relation. But then when it comes time to analyze the data, allow those parameters to be free to get best fitting values according to observations, rather than sort of taking literally the deconvolution result from abundance matching. So I have sort of dual purposes in sort of presenting a parametric form of abundance matching here in this lecture. Okay, so this is the sort of last slide from this lecture before I switch to a Colab notebook. What I've done is, with the black dotted points in this figure, I have taken measurements of the stellar to halo mass relation redshift 0 from the TNG simulation. So the black points the black points are essentially just direct measurements of the mean stellar mass as a function of halo mass at redshift 0 in lustrous TNG. And I've built an approximate model, a smooth parametric model for the stellar to halo mass relation. And I just took a random guess for what the parameters should be to sort of roughly give me a curve of the right shape. That's what's shown in the dashed blue. And then I've derived a best fitting model via an exercise in gradient descent that I'll sketch for you in the Colab notebook. So a few quick words about gradient descent. But actually, I think now might be, in case people have a burning question about the stellar to halo mass relation, I'm going to abandon ship on abundance matching and really start talking about differentiable techniques for optimization. And so in case there's a burning question people would like me to address now before I change gears, this would be a good sort of pause moment in the.
Right. When you showed the peak in star formation efficiency, we know that cosmic noon happens at Z2, right? And halo accretion probably peaks around protocluster accretion at 3 to 4-ish. So is this peak, is this sort of similar star formation efficiency throughout redshifts consistent with any observational data that we see?
Wait, sorry, I missed an important phrase. So you said something protocluster mass accretion rate peaks.
So this is star formation rate divided by halo mass accretion, right?
Right.
So star formation rate, we know from observations that it peaks at Z equal to 2, which is cosmic noon.
Okay.
Right. And
right.
Halo mass accretion probably peaks slightly before. I don't think there's a specific redshift that I'm aware of, at least, but it probably peaks slightly before. So how is this consistent with the observational things that we know about, say, cosmic noon and other things?
So it is. So let's see, two-part answer. So yes, it's consistent, and it's actually, when you say that the star formation peaks, what you're actually referring to is the cosmic star formation rate density. So just the star formation density of all galaxies in the universe, and it's true that peaks around redshift 2 or 3. So This refers to the, yeah, so before I get to that part, so there is no such peak in halo mass accretion rate. There's no such peak.
Okay.
Halo mass accretion rate just scales monotonically with halo mass. And so it is actually galaxy formation physics that leads to the star formation rate density peak at higher redshift. And that feature is not present in dark matter halo accretion rates across time. So that's an emergent phenomenon. And this simplicity in the characteristic peak at 10 to 12 halo mass is something that emerges from galaxy formation physics and is not something that is sort of present at the n-body level at all. So
Okay. Thanks.
Great.
Hi. How many free parameters typically are there in these parametric sham models compared to like HOD models?
So it depends on what range of mass that you're trying to fit. So the parametric model that I will show you here has 5 free parameters. And the most sort of vanilla, simplest HOD models have 5 parameters. I'll talk a bit about the HOD, or actually at some length in the next lecture. So just 5 to 5 is a kind of misleading comparison because the HOD only describes the population statistics of galaxies more massive than some threshold. HOD galaxies have no attributes. They just either are in the sample or not in the sample. Whereas here you have an actual continuous value of stellar mass that you're predicting. And so stellar to halo mass relations that sort of in that way are more predictive than an HOD.
One more question over here. So I had a question about, so the star formation efficiency plot. I might not be understanding it completely. Could you explain why from 10 to the 14th to 10 to the 15th halo mass, we see basically this, maybe I'm misunderstanding this, but it seems like the star formation efficiency plummets.
Right.
Why is that happening?
So in very high mass, well, so the physics of why that's happening is probably to do with AGN. It's also important just to keep in mind that, so what I mean particularly by star formation rate, so I also mean in situ star formation rate. So at very high mass, actually most of the stars that belong in, that sort of are bound to a cluster mass halo were formed ex situ in smaller galaxies. And then they were brought in as a result of a merger. In fact, most of the stars that were formed they're found in cluster mass halos were formed in Milky Way mass halos because most stars were formed in Milky Way mass halos. And so the star formation efficiency as plotted here takes that into account because it's to do with in situ star formation efficiency.
Okay, thank you.
I have a question about the comparison that you have between Illustris and Illustris TNG. I was wondering, like, so Illustris TNG, I think, like, includes magnetic fields as like Illustris doesn't. Is there anything else that Illustris TNG includes that makes this, like, relationship like fit?
Yeah, so it's very many things. So it was not just a single knob. It was even also a revisitation of the solver and both at the high mass end and the low mass end, some reimplementations and some straight retunings of parameters. So it's many things at once. It is not just simply like MHD, for example. So yeah.
And also, what is the resolution that it's used for, like, the hydrodynamical simulations here?
Let's see. Can I carry around? I don't carry around TNG's mass resolution. It's a little better than 10 to the 8 solar masses, but better than that. To give you a more accurate answer than that, I would rather not do that while I'm on my feet, especially if someone in the room is like working with TNG. So
yeah,
no problem.
Right. Yeah, okay. Thank you.
Okay, I would like to. Okay, so we can definitely talk some more about stellar to halo mass relation questions in Q&A. I would like to move on to methods of solution of gradient descent using differentiable libraries. So the basic idea behind gradient descent is you have some sort of loss function or some cost function which tells you how good your fit is to the data. You take the derivative of that loss function with respect to your parameters, and then you take one tiny step in that direction, recompute your derivative, then take another tiny step in that direction and continue down the loss curve until you find the minimum. So there are many people in the room have likely used very fast implementations in SciPy of optimizers. And what I'd like to show you is a way in which you can use the JAX library for automatic differentiation, which I'll tell you about in a bit, to perform your own gradient descent from scratch that gives essentially identical results to what you get from a canned library like SciPy. So let's see. First, so in this cell, I do a few imports from JAX that should just work out of the box in Google Colab. But if you're going to do this on your own sort of separately, then you may need to set up a Conda environment that will be compatible with the rest of your libraries. So JAX is a fast-moving library, and that can be a bit tedious. Colab makes that easy. So all that's going on here at the windup is I'm just loading in some simple ASCII data and just making a plot of the stellar to halo mass relation from TNG. And again, I just lifted this directly from Annelise Pilepich's paper. So what I'm going to do next is define a toy model of the stellar to halo mass relation. So what I've done here is really just, I've sort of defined a custom sigmoid function. A sigmoid function is, it's like an error function. It asymptotes to one value at low x, one value at high x, and then smoothly interpolates between the two. And I've used a sigmoid function to define the slope of a line. So this model of the stellar halo mass relation is just a line with a smoothly varying slope. Nothing more to it than that. So predict log SM just takes in the model parameters that define the sigmoid and the value of halo mass, and then it just spits out the stellar mass. And I use sigmoid functions a lot. It's my favorite function in the world. And so just having done that a lot, I was able to take a reasonable guess for what the stellar to halo mass relation should look like based on some sort of hand guesses for what those initial parameters would be. And I did okay. It's not a great fit. I wouldn't try and interpret DESI data with a model of this quality. Okay, so far so good. Now I would like to define a loss function. And I'm going to do that in terms of the mean absolute error of the difference between the blue curve and the dotted points. So here's a generic implementation of mean absolute error. And then the loss function, all it does is it takes in the target data. It computes the prediction as a function of whatever parameters you gave it. And it takes the mean absolute error of the difference between the prediction and the target. And then that's it. So here my initial guess has this value of the loss. And here, using the magic of JAX's implementation of automatic differentiation, I now define, using JAX's grad function, I define the derivative of the loss function that I implemented. And notice now my new function takes in the parameters, it takes in the target data, and it tells me the derivative of the loss. And it returns an array of 5 numbers because this is a 5-parameter model. So how did that work? I have some slides to follow this particular notebook to explain what it is that's actually going on under the hood with automatic differentiation. If you haven't seen that before, it should look like magic. It did to me. That I implemented a function in JAX just like with a couple of these little just-in-time decorators, and then I just called the grad of that function, and all of a sudden what I got back was a function that is the derivative of the function that I implemented. So to me, that looked like magic. And some years ago when I started using JAX, when I wrapped my head around how powerful that is, I basically stopped what I was doing in my research. I ignored all the previous code that I'd been writing for years. And then I just started doing this from scratch, rewriting many of the things that I'd been using for years with sort of noisy Monte Carlo realizations that were not differentiable. It's a very powerful tool, not just for the galaxy halo connection, but scientific computing, broadly speaking. Okay, so now I want to use this derivative in one of SciPy's canned optimizers, so the SciPy minimize function. So SciPy's minimize function gives you many different options for what optimization routine that you can use. You pass it the function, you pass it the initial guess, whatever arguments your loss function accepts. And then here, look, I'm passing my derivative function to the Jack argument. This stands for Jacobian. So SciPy has a set of routines that can optimize a function for which you supply a gradient in addition to the function itself. One of these methods that's particularly good in tens of dimensions is the BFGS optimizer. Can I just, would you all mind if giving a show of hands? First, a show of hands, have people used SciPy's optimize routine before? And has anyone ever, when you have done that, have you ever used the Jack argument before? Okay, so a few of you, okay. So earlier, so at several different times actually in this summer school, we've heard I've heard reference to the Atom optimizer, which is still, I think, the sort of gold standard in neural network optimization. So if you have a model of 1 million parameters, Atom and small variations of it are still the best game in town for optimizing a 1-million-dimensional function. To get the derivatives, you essentially use what's called back propagation. Automatic differentiation is really a generalization of backpropagation. And the BFGS optimizer is basically useless in 1 million dimensions. But I mostly just wanted to call your attention to the fact that what optimizer you use that's best for your problem depends entirely on the dimension of your problem. So it is definitely true that that BFGS is useless in 1 million dimensions and Atom is the best game in town. But if your model is 10, 20, 50, a few hundred dimensions, then BFGS blows Atom out of the water. It's not even close. It's a much more sophisticated algorithm. It tries to make guesses based on the second derivative. So if we pass our derivative function to this Jacobian argument, we can use the BFGS optimizer. And this functional form is excellent at giving a good approximation to this particular scaling relation, the TNG stellar to halo mass relation. So there's BFGS at work with your automatically differentiated function. And now I want to show you how you can just roll your own gradient descent so that you don't need to use SciPy at all. Because you now have a gradient, then you can just take your own little steps in the direction of towards the global minimum. And I would like to show you how easy this is in case you haven't done it yourself before. And this is a good example of how I think it's very helpful to roll your own routines and write them from scratch for purposes of learning, of understanding how gradient descent works. And then you have a better understanding of what's going on under the hood inside, much more highly optimized routines like that are in SciPy. So it really is as simple as taking a tiny step in the direction of the gradient. So notice all I'm doing here, these few lines are a drop-in replacement for calling the SciPy optimize.minimize. So you have some initial guess. You take a bunch of steps in a naive for loop. At each step of the for loop, you compute the loss and its gradient. And you update your parameters by taking one small step in the direction of the gradients multiplied by what's called the learning rate. So the learning rate is just some fractional multiple of unity that says take a tiny step in the direction of the gradient, not all the way in a unit step. Rinse and repeat for many steps. And then at the end, let's get a best fit. Let's just see how our prediction for the best fit stellar to halo mass relation did. And it's right on top of the SciPy value. So we essentially recreated from scratch the our own gradient descent that is entirely comparable to the results that you would get from SciPy, but you didn't need an external library except for automatic differentiation. So this is a sort of simple demo of what you can do with gradient descent that is especially powerful if your model has more than just 5 dimensions, but it's easier to wrap your head around, I think, for a toy problem for purposes of getting a demo to see how gradient descent works, doing it yourself from scratch. So I haven't said anything about automatic differentiation yet, other than to use that jargon term and then to pass right over it as if it were meaningful, and it might not be in case you haven't heard that before. The rest of the lecture, I guess I would like to give you an overview of AutoDiff, and maybe I'll just quick pause to make sure that so far this sort of motivating demo has made sense before I go to the AutoDiff portion. Great. Okay. So automatic differentiation. This is really what's going on under the hood. This is one of the core technologies that makes all of AI possible. So if artificial intelligence algorithms very generally have extremely high dimension, and think for just a moment how impractical it would be if you needed to run a gradient descent algorithm by optimizing a million dimensions or a billion or a trillion for sort of future LLMs using finite differencing derivatives. So for every single parameter, you would need to take a step up and a step down in order to compute the derivative in that direction. And then you would need to do that a million different times for each parameter, for the point in parameter space that you are, and then take one step, and then do that again for another million parameters. So fundamentally, finite differencing derivatives do not scale well with the number of parameters in the problem. And so automatic differentiation gives a programmatic solution to that entirely changes the scope of what can be done with a universal fitting function like a neural network. So I'm going to show you, when I talk about AutoDiff, I talk about it as synonymous with JAX. JAX is what I know, and you can only teach what you know. But there are essentially every major AI/ML library implements their own implementation of AutoDiff in some way. And so JAX is not unique in this respect. Okay, so differentiation comes up all the time in physics. I've motivated the applications of AutoDiff by gradient descent. But for example, I use AutoDiff when I'm just implementing basic models of physics. So for example, I have a model for the evolution of dark matter halo mass. And then simply by implementing it in JAX and taking its gradient, straight away I have a machine precision accurate model for the mass accretion rate of the dark matter halo. Then there are really countless different examples of ways in which differentiation crops up in physics. I want to give you a contrast between, to help you understand what AutoDiff is, I want to first sketch what AutoDiff is not. So AutoDiff is not analytic differentiation. So it is a completely different algorithm. Of course, there is only one correct answer for what the derivative of a function is. And so it must be giving the same result in some way. But I want to highlight that AutoDiff is not analytic differentiation. So imagine you have a complex function, not even that complex, but this function f of x is just the sequential multiplication of several different functions. Imagine computing the derivative of a reasonably complex function implemented or defined in this way. You will find that you will recompute the same terms over and over and over again. So g prime of x times huv, and then h prime of x times guv, just applying a simple chain rule. So for very complex functions like a neural network, you can imagine how many times you would be recomputing the same thing over and over and over and over again. So even though, of course, analytic differentiation gives you the correct answer, there is only one correct answer to the derivative of a function. It's very computationally inefficient for complex functions. Numerical differentiation is also not what AutoDiff is doing. So any function, any smooth function, its derivative can be approximated to arbitrary accuracy through numerical differentiation, just by step up, step down, divide by the step size. But again, this is grossly inefficient with the dimension of the problem that you're trying to optimize. To the point where numerical differentiation, there would be no artificial intelligence that would do anything useful if we had to rely on numerical differentiation to optimize neural networks. Okay, so those are some things that AutoDiff is not. What is AutoDiff? AutoDiff is essentially a numerical derivative of your computer program. It is essentially differentiating the flow of bits of information in your program from input to output. So here's the core idea of autodiff. So every single computation that you use your computer to do, whether it's trigonometric functions or exponential functions, very complex high-dimensional functions, very nonlinear functions, ultimately all reduce to a set of small operations that actually happen on the compute register, on the chip. And your compiler knows how to translate a very complex nonlinear function into a set of those elementary core operations that happen on the register. So those are operations like x goes to x plus 4, x goes to 2 times x. Those operations, you do have elementary expressions for what the derivatives are. The autodiff algorithm builds up a computational trace of the flow of bits of your computer program from a set of inputs through all the different nonlinear operations that happen, decomposing those nonlinear operations into the elementary core operations that happen on the register. And at the end, once that trace is then built, then it is a straightforward but very laborious computing task to just programmatically compute what the derivative should be. So in this way, you do not need to step up or step down. You do not need to know what the analytic expression is for the derivative, but you can get a result for the derivative of your function, which agrees to machine precision, whether that's single point or double, with the result that you would get from analytic differentiation. And it doesn't scale with a number of parameters. You pay a one-time cost for computing this computational trace of your program. And then whether your function is 20 dimensions or 20 million, your derivative then is the same, and the compute cost doesn't increase. So this is the sort of remarkable feature about autodiff that makes it practical to do high-dimensional optimization. Let's see, what are some other advantages of autodiff? So I have been talking about autodiff as sort of something that we use for neural networks, and that's, of course, that's true. Optimizing a neural network without autodiff would be completely impractical and hopeless. But there are many examples in physics where even just a few tens of dimensions seem completely impractical for purposes of a problem that you're working on towards your dissertation. But if you use autodiff, all of a sudden, just like flipping a switch, you can get a perfectly optimized function without having to wait more than a second. So the way I like to think of it is that these optimization techniques that were built to optimize neural networks, if we implement our physical models using these libraries with this technology, then sort of advanced gradient descent methods, you just don't even need to roll out of bed in order to optimize the function. They scale well to 1 million dimensions. They scale great to a smooth physical model in 20 dimensions. So a lot of my sort of graduate, even postdoc years, I spent like building models and then wondering, okay, I can improve this model if I add a little more physical complexity into it, but is it going to be worth it? Are my chains ever going to converge? Am I ever going to be able to optimize this model? These extra 3 parameters, like, are they worth it? If you implement your model differentiably, you don't even need to think about this. There will be no problem at all to derive a best fitting solution. You can just programmatically compute the derivative and carry out gradient descent. And it just really lets you focus on the physics. It really helps you just focus on the quality of the model rather than on whether or not you're going to be able to optimize it. Of course, you still need to have a good physical model in order to have a good result. But it really, if you pay the cost of sort of getting dev'd up to either use JAX or PyTorch or some other autodiff library, if you pay that cost of sort of picking up that skill set, then it really opens up a whole world of complexity, of sort of physical complexity you can capture that was just previously hopelessly impractical. And so that's really, I think, that's really what I think I would like to impress upon you, is that if you're able to implement your physical model differentiably, it completely transforms the scope of what you can do. These techniques are useful in tens of dimensions, not just 10 million. So I've also been describing these advantages in terms of optimization, in terms of gradient descent. But the same is also true if you're interested in inference, Bayesian inference. Already, if you've ever tried to run MCMC on a 20-dimensional model, it's very hard to get converged chains. Modern methods that use gradients for inference for posterior sampling, like Hamiltonian Monte Carlo, scale well to hundreds or even thousands of dimensions to get deeply converged posteriors in a tiny fraction of the compute time. I think I'm probably running almost out of time. And I'm actually done giving you an overview of AutoDiff. So it's not possible for me to really give you an in-depth description of the many, many different sort of advantages and details that are relevant to automatic differentiation. But I do, on my slides, have a bunch of links that I hope can help you, if you're interested, sort of pick up more of this material. So quick overview of that before we break for Q&A. So my favorite way to sort of pick up this material is this differentiable programming tutorial for a sort of a JAX-based implementation of AutoDiff. All of these are JAX libraries. All of these are JAX tutorials. So again, that's what I know. So that's what I can teach. So I also have a lot of sort of publicly available on my GitHub page gists of just sort of different example uses of AutoDiff. And so I have one that, here, this one here covers a bunch of different basic core features of JAX. And so personally, I think this differentiable programming tutorial is more thoughtful and pedagogical than what I put to here. This is a much more Andrew-centric overview that gives some complementary information. So this just shows an example that I sort of sketched of how to build a model for dark matter halo assembly, where you get the derivatives for free, the mass accretion rates for free. If JAX also has, you can also solve ODEs so directly in JAX. And the really cool thing is that if you solve a differential equation in JAX, you can differentiate through the solver so that you know, for example, how the solution space depends on the initial conditions and optimize, and then run a gradient descent on that. And then I conclude with just two very low-level introductions to how to sort of implement neural networks in JAX. These are now dated because there are more modern libraries that are much more powerful than the ones that I linked to here. These are the bottom two. The first one doesn't use a library at all. So the first one I just show you using elementary means how to write your own neural network, just a simple multi-layer perceptron, just a few dense layers, and how to optimize that using your own home-rolled gradient descent, so that you can really sort of see under the hood, like what it is that an MLP is doing, and really how simple the technology is. Like how if you, just with a couple of simple for loops and then using AutoDiff, you can write your own neural network from scratch, and then optimize it yourself from scratch. And then in this final one, I show a relatively low-level library for using JAX to build up much more sophisticated neural networks, and then optimize them using a modern implementation of Atom, as opposed to your own fixed learning rate gradient descent. So yeah, I think maybe I'll just conclude here.
Yeah, maybe we can have time for one or two questions before breaking.
Right. Thanks for the talk. It seems very, very interesting technology. It's very impressive. So I was wondering while we were talking, is that how you see the field changing in the future with that? Is that'll be a case that we might replace like camp and class instead of seeing Fortran, just like rewrite everything, then you have many parameters as you want to fit a model, then it'll be just fast.
So there actually already is a differentiable implementation of class. I am in the space of this Q&A. I am forgetting the lead author on that, but I will follow up on Slack on that particular implementation. But the future is already here. So there are many papers that essentially do a complete rewrite of some existing code using differentiable, very commonly JAX code. So for example, JAX Cosmo is a library of many common cosmology functions that is now fully differentiable in injects, and then let you use Hamiltonian Monte Carlo in your sampler. I wrote a library on stellar population synthesis called DSPS for differentiable stellar population synthesis. That's also implemented in JAX, so you have differentiable photometry predictions. One advantage that I regret I'm only just thinking of to now to mention of using AutoDiff is that all of these AutoDiff libraries were written to run on GPUs and to scale on GPUs. And so a major computational advantage, even if you ignore gradients, is that all of a sudden, just by implementing your function in JAX, all of a sudden your code is GPU fast. So for example, the stellar population synthesis library that I wrote is 300 or 400 times faster than leading libraries of SPS. Just simply by re-implementing the same calculations on a GPU, the compute power that you get for free for the cost of rewriting all this code is very, very powerful. And so I think that future is not just coming, it's already here.
Thanks.
Yeah. Oh, and then one more response to that. So yes, it's true that that as you can increase the number of parameters and you can have as many parameters as you want, and you won't have any trouble optimizing the function. Of course, that doesn't change the essential fact that you may have degeneracies in your function, in your model, that are then that obscure the actual underlying information content that you're after. So this doesn't change those rules. Those rules are inviolate. But what it does is make it practical for you to test whether or not expansions of your parameter space are worth it. So.
Can I have a question? So thank you for your great talk. And this could be a basic one, but what is the main difference between the subhalo abundance matching and between the subhalo abundance matching and halo abundance matching? So because yeah, I know the subhalo and halo is both the gravitationally bound system, but I think it has a different physical properties. So what would be the main difference? And I suppose there are some points that we should care about when we deal with the two things. Yeah.
Right. Great. First, quick clarification. I'm sure I've caused at least some confusion for at least some of you in these lectures when I have glibly obscured the difference between host halos and subhalos by just calling them all halos. And so sometimes I've slipped up and just called it a halo abundance matching maybe, and I have meant subhalo abundance matching. It is. I think that is also a common usage. So people may refer to halo abundance matching, and they typically mean you include the subhalos. If you want this part is not ambiguous. If you want your abundance matching prediction to agree with 2-point clustering on large and small scales, then you must use subhalo abundance matching. Otherwise, you'll be grossly incorrect on all scales, but especially on the one halo term. The reason is just that galaxies live in subhalos, not in host halos. And so if you don't populate your subhalos with galaxies, then you'll be missing an enormous galaxy content. There are examples of actually host halo abundance matching. So for example, if you have a catalog of galaxy groups for which you have done some grouping of observed galaxies on the sky and say, I think those galaxies live in a common halo, and I think those galaxies live in a common halo. Well, that lets me compute a number density of galaxy groups. And then in that particular application, I would want to perform the number density matching on the host halo mass function. Because I've said a bunch of satellite galaxies are grouped in this common halo, and a bunch of satellite galaxies grouped in this common halo. And so I've eliminated the subhalos from the counting and the measurements, and so then I should eliminate the subhalos from the counting and the predictions. And that's actually the way in which galaxy group catalogs most commonly estimate halo mass, is through host halo abundance matching in that way. So does that help?
Thank you.
Great.
Yeah.
Let's thank Andrew one more time. So to make sure we end everything on time, let's be back, take a short break, and 12:05 we start the next lecture.